This video is about simplifying radical expressions. So let's get that written down. Now, when you are simplifying radical expressions, you have to remember that you're looking to find perfect squares. And so anytime you simplify radical, you always want to remove your perfect squares. Now, some perfect squares, you think of, first one is going to be 1, because 1 times 1 is 1. All right? And then you have, so let's think, so that's 1 squared. All right? And then if I think about what is 2 squared, that's 4. All right? 3 squared is 9, and so on. All right? And so you can see the pattern is going to continue. But you're looking at a number times itself to be a perfect square. And it's not listed on here, but 0 is also a perfect square. I mean, because 0 times 0. So numbers you think of is you have to have an even exponent. Right? And thing can also happen when you have variables. For example, x squared is also a perfect square. All right? X to the 4th, x to the 6th. All right? Anything that has an even exponent. All right? These are also perfect squares, because you can always write a number that can be squared. So this is the same thing as if I have x times x, or this is the same thing as 2 groups of x squared, 3 groups of x cubed. And so really when you're looking for your perfect squares, you're really trying to utilize the powers. So the number underneath a radical, so say we get something like the square root of 25. Right? So that's a perfect square. And so we would say that the square root of 25 is 5. And that's usually because we think about saying a number squared is 25. Now there's also rules for radicals and exponents that we've talked about. So for example, the square root of 25, because underneath the radical that's 5 squared, and then using what this square root means, that's the same thing as 5 squared, and the radical is the same thing as the 1/2 power, we can look at this as multiplying our exponents, and that's the same thing as the number 5. So this is another way of thinking about your perfect squares, is changing the square root into the 1/2 power and utilizing powers. For example, say we have r to the 22nd power. Right? So if I think about this, this is the same thing as taking r to the 22nd power and then the 1/2 for my radical. And when I multiply these two together, that's the same thing as r to the 11th. So when you have an even exponent underneath the radical, in reality, you're really just looking at making 2 equal groups, and that is your simplification. Right? So say we put variables and numbers together. All right, so let's do, say, the square root of 144, and I have x to the 16th, y to the 4th. Right? So each one of these is individually underneath the radical. But again, I could think about these as the square root of 144 times my square root of x to the 16th times the square root of y to the 4th. All right? So a rule for radicals is that they can be broken up into individual factors. But again, a number times itself to get 144 is 12. If I think about this square root is going to be telling me I need half of 16, I'm going to get x to the 8th. And this square root is saying half of 4 is going to give me y squared. And so this is what my simplified radical would look like. Now, when you don't have perfect squares, the ones that are not perfect need to stay underneath the radical. for example, if I have the square root of 48. Right? So 48 can be broken up into 16 times 3 underneath the radical. So the individual factors, and you always try to see if you can find one of the perfect squares. But again, this is the square root of 16 times the square root of 3. And since 16 is a perfect square, that's the number 4. But 3 is not a perfect square, and so it's times the square root of 3. And so you could either put the little multiplication symbol here to remind yourself that it's 4 times root 3, or you can just write simply just 4 root 3. As long as you remember that that's multiplication, you don't need to put the symbol. Now the same thing is going to happen when you have variables. So say I have x to the 7th power. Well, your job is going to be to break this up into just having, say, one of the x's and then all of the rest that are the evens. So you really, when you have an odd number, you want to split off just one of them and keep all the rest to be able to use your perfect square. And again, if you really want to, you can split this up so you can see what's happening. Now the square root of x to the 6th, again, that square root is going to say take half of what's underneath there, and that's going to give me x cubed. But I can't take half of 1, right? So that root x is going to stay underneath the radical. So when you have an odd number of variables, right, you're going to pull one of them off and keep the other even ones, and then take your square roots. And so you're going to do this for all of your radicals, you know, no matter what you have on here. Say you have the square root of 54, you know, a to the 9th, b to the 5th. Now sometimes you're not going to necessarily remember what perfect squares are, but if you think about your math facts and you start moving along with perfect squares, right? This is the same thing as 9 times 6. Okay. And then I have an a to the 8th and an extra a. And then I have a b to the 4th and an extra b. And so what I'm doing is I'm splitting up all the individual factors. And so this is another technique you can use, right, is to kind of combine these two ideas. So I've got my 54 that's broken up into a perfect square and a not perfect square. For my a to the 9th, I took one of them off so I have an even number, and same thing with the b's. And so anything that's a perfect square, I'm going to deal with first. So the square root of 9 is 3. Square root of a to the 8th is a to the 4th. Square root of b to the 4th is b squared. And then left underneath the square root is going to be these ones that I haven't used yet. I can't do anything about these because there are no more perfect squares. And so this is going to be your simplified radical.